Good afternoon, everyone, and welcome. The webinar will begin shortly. Good afternoon and good morning to those of you out west. Welcome to today's Ask Me Anything from the Construction Specifier and IAC Acoustics. My name is Farheen. I'm the Associate Editor for the Construction Specifier, and I'll be moderating today's presentation. First, I'd like to introduce our speaker, Andrew Polte. Andrew is the NVH and Testing Facilities Sales Manager at IAC Acoustics. He is a mechanical engineer with more than 13 years of experience in automotive and off-highway vehicle component testing, with a focus on NVH analysis, materials development, and ISO IATF quality manufacturing experience. In this episode of Ask Me Anything, Andrew will showcase the products available from IAC Acoustics with a focus on industrial applications. A review of some examples that IAC has recently provided will highlight the advantages of an effective noise control solution. Some questions for this session have been submitted ahead of time, but we'll also answer any questions that you submit live. To cover a few housekeeping items before we get started, if you have any questions that you wish to submit while following along to this session, please post them at the Q&A located at the bottom of your Zoom window. Zoom does have a raise hand function, but since we'll be keeping everyone's mics muted, only use the Q&A instead. If you're experiencing any technical difficulties, you can enter a message in the chat, which you'll find right next to the Q&A, and we'll do our best to help from there. Today's episode is also being recorded and will be available on the Construction Specifier's website in the near future. Andrew, thank you so much for joining us today. Please take it away.
You're welcome, Farheen, and thank you for that introduction. I appreciate it. Today, we're going to be talking about noise control products, specifically for industrial applications, not necessarily exclusively, but we're going to go through a lot of applications and case studies specifically related to the industrial world. So let's get started. First off, I wanted to just go very, very briefly about some basic acoustic definitions here. Typically, when we're in the world of acoustics and noise control, we're looking at decibel levels, specifically A-weighted decibel levels. And if you see dBA, all that A stands for is a filter. It's a way that we attempt to mimic how people perceive sound, usually at very low frequencies. We're not very sensitive. Our ears are not that sensitive to sound. And so the low frequency energy is filtered out. Typically between 1,000 and 6,000 hertz, roughly, we're more sensitive to sound, so that sound ends up getting amplified. And then there's another drop off again above 6,000 hertz where we just don't perceive sound as loudly as we would for the mid-frequency bands. Just a reference for what a dB is in a normal conversation office type of environment, you would expect to measure somewhere around 60 dBA. Heavy traffic and where we start having to have hearing conservation programs needing to be implemented around 85 to 90 dBA. And then when you actually start to feel pain and cause permanent hearing damage very quickly, somewhere in the range of 120 to 130 dBA. There's different steps to how people perceive sound. Sound difference of 3 dB is very, very small. It's hardly noticeable. Most people won't even notice a difference. 6 dB obviously is a little bit more noticeable. Most people would be able to detect a difference between sound sources that have a 6 dB difference. 10 dB is quite a bit different, and then 20 dB is very, very noticeable. There's a 10 times larger amplitude change from 20 dB difference. Sound can travel through a variety of different paths. When we look at noise control, we're usually focused on that top one there for airborne sound, but sound can also travel through structures, solids, structural steel, concrete. It can travel through liquids and water and things like that as well. There's different ways that sounds are received, either from the source directly, so you have a direct line of sight from the sound source and the receiver. Also through indirect sound sources, reflections from walls and ceilings and floors and other hard surfaces. And then there's indirect sound. Sound actually can bend and curve around buildings and things. And so that would be a flanking noise, where you hear a sound not necessarily through a reflection or directly, but through a curved or flanked path in between two different rooms, for example. There are three different locations that we're able to treat unwanted sound or noise. And the first one's at the source. That's typically ideal. You have a compressor in a factory, for example. That compressor is very, very loud. You can replace the compressor or get a whole new piece of equipment that's treating the source. Along the path is generally what we focus on with noise control products. So that would be putting an acoustic blockade, so to speak, between the source and the receiver. And then the receiver itself, typically, if that receiver is a person, oftentimes we'll have to have the person wearing earplugs or earmuffs to help reduce that sound. So today we're going to focus on the path, along the path. There are two types of ways to reduce sound and noise control. The first one is to apply a barrier. A barrier is something that is solid. It is not porous. It's typically very massive and very stiff. In general, the better the acoustic performance, the heavier and stiffer the barrier is going to be. Very basic way to block sound will get you roughly an STC 20 performance. And we'll talk about STC briefly here, but in a minute. But higher performing systems can block sound with ratings up to STC 55 or even higher into the 60s and even the 70s. The way that we measure how well sound is blocked with a barrier is the STC, but typically that is a calculation from different transmission loss values at different frequencies. So the transmission loss is how well sound is blocked by the barrier at a different range of frequencies. So there's different values at different frequencies, and those ranges of values, the transmission loss values, are calculated and boiled down to one number, and that's the STC. So it's really important to know what frequency your noise is that you're trying to reduce. A very low frequency sound could have a very different solution than a mid or high frequency sound. I mentioned STC, that stands for sound transmission class. And that is, again, a measure of how well the material blocks sound. There's a variety of different frequencies called third octave bands that the sound transmission loss is measured in. And then those sound transmission loss values are calculated into a single rating, which is the STC. It's really important to note that STC is measured in a lab. So the STC value is measured in a very specific way based on the ASTM E90 standard. There's a requirement to have 2 reverberant rooms, and the partition or the material that's being tested is mounted in a frame in between those 2 rooms. So the sound source, typically very large speakers, is on the left side, and then on the right side is the microphone measurement to measure how much sound actually transmits through that test panel into the other room. So it's essentially a simple subtraction the sound pressure on the left side minus the sound pressure on the right side. And that's how those sound transmission loss values are measured. So I mentioned there's two types of noise control solutions: barriers and then absorbers. Absorbers you can think of as almost the opposite of a barrier. They're very soft, they're very porous, or they can be open-celled. Foam is a good absorber. It's very porous. It has a lot of bubbles in it. Fibers, mineral wool and fiberglass would be more of a non-woven or fibrous kind of absorber, but the basic function is the same thing. Sound enters the absorber and then it gets dissipated from mechanical heat or mechanical vibration from the absorber and heat. So the sound is dissipated through the absorber. The way that we measure noise, the ability of an absorber to capture that sound and dissipate it is called the NRC. That stands for noise reduction coefficient. And the NRC values are determined by, again, it's a specific test that measures how well sound can be absorbed by a specific material. In theory, the NRC value of 1 would mean that the sound is being all absorbed all the way. However, because of the test method, the way it's set up, and because of some of the different effects during the test that happen around the edges of the material, you can get NRC values of greater than 1. I've seen 1.3, 1.4 possible. So it's just important to note that. And again, this is a laboratory test based on ASTM C423. The NRC value is calculated from very similar setup to the STC. However, this is only needed in one room, and the device under test or the piece of material that's being tested is placed on a hard surface. Usually it's on the floor, but it could be on a wall or some other surface. And then sound is emitted in the room. The speaker's turned off, and then the decay or the measure of how much echo is in the room is measured and calculated, and then the slope of that decay determines what the NRC value is. Now, oftentimes in noise control, we use a combination of barriers and absorbers, and there's plenty of products out there that offer both functions. They're multi-layered systems, and that's what we would call a composite material. In this example on the image here, you can see on the left side, there's an exposed quilted panel. That would be the absorber side. And then on the right side, there's a vinyl layer there that would be the barrier side. So we'll get into the actual noise control products now, that we can talk about the various ways of treating sound depending on what the source is, what the target is, and termination of the source, the path, and the receiver, what's going to be the best method to block sound or absorb it. Flexible noise solutions are often used. Quilted fiberglass, vinyl barrier back fiberglass are really big in the industrial world. Typically, the barrier is going to be a vinyl that comes in different thicknesses depending on how much sound you need to block. They're pretty heavy duty. There's applications and specific products for both indoor and outdoor applications. You can have them temporary, or you can have fixed permanent solutions with these curtains. A lot of different options there, different sizes and shapes and colors as well. Typically, they have grommets in them, which you can kind of see in the image on the top. So oftentimes they're hung either from a ceiling or from a steel structure. But they can also be placed directly onto a wall as well. With a curtain enclosure, you can get usually between 15 and 20 dB of reduction. If it's just a wall partition or a wall enclosure with minimal openings, oftentimes it's around 10 to 15. But if you have a full enclosure where you have the walls and the ceiling, maybe a sliding curtain, for access, you can get up to 20 dB of reduction. Here's some images of some outdoor applications, all the way from on the left side, somebody's backyard, up to huge industrial applications where you have multiple levels of curtains at very tall buildings. And these are often used on construction sites, especially near residential areas and apartment complexes and high rises, things like that, where you have construction that might be happening for several months. You don't want to disturb the neighbors and folks that might be in the areas. Oftentimes those are temporary solutions. So these curtains are really easy to install and take down, and they can be reused. Another noise control option is duct wrap. A lot of times, especially in oil and gas industry, you have very large pipes and very large ducts. Sometimes they can be next to facilities or parks, things with people around them. They need to be quiet, and duct and pipe wrap is a very simple solution. It's a flexible, reinforced, typically it's foil face loaded vinyl barrier, and it just wraps around the pipe. You can wrap it around circular or rectangular or square pipes, and usually it's 1 to 2 inches thick, roughly, and it's generally a composite. So you'll have a vinyl barrier, which is the black part down here in this image, and then the absorber, which is like a fiberglass or a mineral wool on the inside. HVAC silencers are very commonly used as well. They provide a minimal pressure loss if they're designed properly, but still are able to mitigate quite a bit of sound. Factors like the airflow requirements, how much airflow needs to go through them, the amount of sound that needs to be reduced. Those are the two general factors that are used in designing how large and how long these HVAC silencers need to be. Another HVAC option is louvers. Louvers are essentially a thin version of an HVAC silencer. You can be as much as 24 inches thick, or all the way down to the slim 4-inch version for the acoustic louvers as well. They typically offer a lot more resistance. There are a lot of outdoor applications use acoustic louvers, which is actually, I think, what all of these images are for outdoor applications, as opposed to the silencer. And if you're restricted in space, you can't afford to have 10 feet of HVAC silencer, then the acoustical louvers can be a pretty good solution. There's metal wall barriers as well. Oftentimes these are outdoors. Actually, most of the time they're outdoors as well. They're commonly used for HVAC chillers, either ground mounted or roof mounted. Typically there's a barrier that's placed as close to the HVAC chiller as possible. They're used for electrical transformers as well. They can be used for a variety of different applications, either on the roof of an existing building or on the ground. Battery storage facilities use barriers all the time as well. Very similar. They have very similar types of sound issues as electrical transformers, where you have that continuous humming. So these are pretty frequently used. You can paint them any size or any color that you want them to be. The heights can be very, very tall, several stories high if necessary, and they come in a lot of different thicknesses and sizes. Similar to the enclosure. So for metal noise enclosures, these are used in a lot of industrial applications. Factories, research and development and testing facilities will use these metal noise enclosures. There's a huge range of applications for here. The images here just essentially show some examples, but oftentimes these are used for machinery enclosures. We use metal noise enclosures for acoustic testing facilities, reverberation rooms, anechoic chambers, rooms that require different levels of reverberation time, and adjustable rooms. They're typically a single wall construction, but if there's a very high level of noise reduction needed, they can be double wall as well. So it's essentially a room within a room. Control rooms are used all the time. Use these metal wall enclosures as well. You can get up to STC 70 with the double wall room, and the NRC values can come up to 1.1 or even higher if needed. If you have a facility that's already built and you're just looking to reduce the echo or increase the absorption coefficient inside the space, especially for swimming pools and gyms, those are some of the more common applications. But really anything that has a large room with a lot of hard surfaces, you're going to have a lot of echo. And so fabric wrapped acoustic wall and ceiling panels can be an economical way to address those issues. And these come in typically 2-inch or 4-inch thicknesses, depending on how what your acoustic requirements are. They can be mounted on the ceiling or on walls as well, as shown in the images. Similarly, if you need something a little more durable, metal wall panels will provide a very similar acoustic performance with a little bit more aesthetics. There's typically the V-groove, which is what's shown here, can have a little bit of a little surface variety here instead of just a flat panel. They're very, very low maintenance. They are non-combustible. It's essentially metal powder coated, metal perforated, wrapped with a insulation. They're very durable and very economical. The standard thicknesses for these are 2 inches or 4 inches, and you can get up to NRC values of 1.2, 1.25. Acoustic ceiling tiles are very similar to the perforated wall panels, but they're specifically designed to be offset from the mounting surface. You can also put them, we can design the perimeter to fit into a 2x2 or 2x4 lay-in grid, an existing ceiling tile grid. And again, these have NRC ratings up to 1, potentially a little more if required. Oftentimes they come with a 1-pound foil-backed vinyl noise barrier as well, so that we can turn the ceiling tiles from an absorber to a composite, which would have both STC and NRC properties. Then we have doors and windows. Typically, those are integrated into the metal wall or the metal enclosures, metal barrier and absorber enclosures. The windows can come up to STC 59. Typically, we use a laminated safety glass, but we can put polycarbonate in there. We can put one-way mirrored glass in there. BRG or bullet-resistant glass is another option. And so there's a huge range of versions. Actually, the image in there shows a slanted window, which helps to redirects the sound reflected from the window up to the ceiling. So that's kind of ideal if you're trying to minimize reflections and not have so much echo in a room in some test, like a test facility or a recording studio, for example. And then we have doors. The doors can be acoustically rated up to STC 64 for a single door. There's a variety of ratings that are offered: RF rating, fire resistance, or UL rated doors as well. You can electrify them with magnetic key readers, power transfers, and operators. And there's also some blast and bullet resistant versions as well, if that's what's needed. Okay. That's all I wanted to go through briefly. And so I was hoping we'd have quite a bit of time at the end for questions and answers. If anybody has any questions, feel free to send them out.
Thank you so much, Andrew, for this excellent presentation. As mentioned, we do have some submitted questions, but we'll also take any questions you want to submit during the course of the session. So just be sure to post any questions you have in the Q&A located below. First question is, what are the best products and practices for mitigating sound flanking over demountable partitions abutting lay-in acoustical ceilings?
Yeah, so acoustical ceilings, there's a huge range of acoustic ceiling tile manufacturers and material providers out there. I think the key is if you're trying, so that tends to be a flanking issue, right? If you have sound coming from a different room, it can transfer to another room, either through the HVAC ducting or through the ceilings itself if the ceiling's not treated well. For ceiling tiles, you want a composite. You want to have a combination of an absorber to help absorb the sound that's in the room, but also a barrier to make sure that the sound that's coming from a different location outside of that room doesn't come in. I think that might be the answer to your question, hopefully. If not, let me know and I can follow up and clarify it.
Thank you so much. Next question. What is the best economical acoustic treatment for wood shop, but also restaurants?
Yeah, wood shops. I've been into quite a few wood shops before, and the big source of noise is the vacuums, the dust collectors. Those can be pretty loud. Sometimes they'll have mufflers on them, but usually not. The best way is to treat the source, obviously. So if you can enclose that vacuum pump into some, basic enclosure, either a hard panel enclosure with a couple of inlets and exhaust penetrations, that's a good way to do it. You can also put a curtain enclosure around it as well. But if there's no solution for that, oftentimes these wood shops are drywall, or they'll like a metal corrugated roof, and so they're very reflective. So you can put absorbers on the walls and the ceilings to help knock down some of those reflections and reduce the sound.
Thank you so much. And would this also be applicable to restaurants?
Yes, exactly. Same type of thing. I've actually, there's quite a few restaurants recently I've noticed that have some sound mitigation. A lot of times restaurants will have fairly high ceilings, and they'll be very, very reflective. So ceiling baffles is going to be a really good solution to help reduce the din from everybody talking a lot. And if you can treat the ceiling with baffles, and you can treat the walls with some sort of absorption. In restaurants specifically, aesthetics is really important, and so you could use a combination of fabric wrap panels or metal perforated panels that might have some stylish colors to it. But we can do a lot of different shapes and any color you want.
Great, thank you for answering. Next question. Do you have acoustical solutions for noise generated by outdoor pickleball and basketball courts?
Yeah, especially, so basketball is one thing, but pickleball is a whole nother ball of wax. Usually pickleball courts are just like a chain link fence, right? So the most economical solution would probably be if you already have an existing fence, you can hang some curtains, vinyl back curtains on there. One thing to note about that is not necessarily specific to a pickleball court, but just in general, the sound source should be facing the absorber side. So you'll have the barrier on the opposite end side, and then the perforated or quilted absorber should be facing the source. So as long as that chain link fence is tall enough, when the people are hitting that pickleball around, that sound's just gonna resonate right through the chain link fence. But if you put a barrier and an absorber along that fence, then that should do a much better job to contain that sound within the court.
Great, thank you so much. Next question. What are manufacturers of acoustic barriers doing to remove red list chemicals and make their products healthier? For example, K13.
That's a good question. I don't know if I have a direct answer to that. I'm not as familiar with the K13 and the specific materials that are on the red list. I do know back in the day, there were some acoustical, fiberglass products that were compressed with some resin. They might have had some formaldehyde in them. I haven't seen that for a very long time though, so I think most manufacturers are going away from those kind of materials. It's pretty straightforward with the materials that are used oftentimes for noise control though, for absorbers specifically. It's fiberglass or mineral wool most of the time, and there's typically not a whole lot of additives to that. I know that foam specifically for acoustic chambers, 20, 30 years ago, we would use polyurethane foam, and that would be a lot more combustible and can be pretty toxic when it catches on fire. We're kind of moving away from that and going towards more of a it's called melamine foam, and so it's much more fire resistant. It's a Class A fire resistant product, and that's what we use now for anechoic chambers, for example, that require foam wedges. We'll use melamine foam for most applications.
Great, thank you so much for explaining. Next question. What do we need for sound control for animal shelter outdoor kennels?
Oh yeah, good question. I imagine it's probably pretty similar to like pickleball, right? You got a chain link fence, everything's enclosed, but there's you keep the dogs in, but you don't keep the sound in. So putting some sort of barrier backed absorber on those kennels is going to be important. And you can use a barrier wall where you have a freestanding structure. That essentially remove the line of sight from the kennel to whatever neighbor has to hear that all the time, or you can enclose the entire thing, the entire kennel as well.
Thank you so much. Next question. What's more effective, custom jackets made for HVAC compressors or sound blankets hung around outdoor HVAC equipment screen wall?
Yeah. So both of those would be effective. A rule of thumb that you always want to keep in mind is when you're treating a sound source, you want to get as close to that source as possible. Ideally, you want to be able to cover it up right on top of everything, but obviously for maintenance purposes and we don't want to overheat the system. So I think the jacket's going to do a really good job as long as you can make sure it's enclosed as much as possible, because it's going to be much closer to the source than putting some treatment a few feet or a few dozen feet away.
Thank you so much. What acoustic solutions with SEC and IAC ratings would you recommend for wood-framed multifamily projects?
Yeah, wood frame projects. Yeah, so that's typically going to be drywall, right? So absorbers are going to be really helpful in that situation, and ceiling tiles, the noise foil panels that I was showing earlier. See if I can go back to that. Yeah, these kind of things. When you have a room with absorption, I don't know if you move into a new house and it's like a wood or vinyl floor, before you put all your furniture in there, there's a lot of echo, and it sounds kind of funny. But as soon as you start putting couches and rugs and other furniture in there that will absorb some of that sound, it actually reduces the echo in that room quite a bit. So it's the same kind of application here. If you can cover some of that surface area in these buildings with an absorber of some kind, like a fabric panel or these metal perf panels, then you're going to be, it's going to make it a little more comfortable.
Great, thank you so much for explaining. Next question, can you provide a description of test facilities and latest developments in fibrous materials flow resistivity, acoustic impedance for LF performance?
I'm not sure what LF performance is. I am a bit familiar with flow resistivity and acoustic impedance measurements. So let's go back to this. This NRC value that I mentioned earlier is calculated in a reverb room. So essentially what this does is it blasts sound in all different directions on this specific material. What an impedance, acoustic impedance, is typically done in an impedance tube. So essentially it takes the sound and directs it normal to the surface of the material. So you only have sound coming in one direction. It's really good for a quick measurement, and you don't need a lot of sample size to be able to do this and get some values in. That's pretty common. I mean, I have seen there's a limitation with this method with the impedance tube. You can't really get a good measure of acoustic performance above 5,000 or 6,000 hertz unless you have a really tiny small tube. But I have seen some folks working on that now, being able to get absorption measurements up to 8,000 to 10,000 hertz. So there's a little bit of work that's being done on that. It's not real standard, but that's kind of a big limitation. Most of the time, when you see these NRC values, they'll only go up to about 4,000 hertz. And then flow resistivity, it's just another way to measure sound absorption. And it's, that's test method's been around for decades. And as far as I'm aware, there really hasn't been too much change from that method.
Thanks, Andrew. LF might be low frequency, is what an audience member is saying.
Aha. Okay. Oh, there it is. Yes, thank you. Okay, so for low frequencies, yeah, the impedance tube has its limitations on low frequency. I mean, you can build a very large impedance tube, and that's been done in the past, especially when we look at anechoic chambers, for example. We have something called a cutoff frequency. And what that is the lowest frequency that you can accurately measure inside that room. So it's based on the depth of the material treatment, and also loosely based on the volume of the room as well. So if you need a very low frequency cutoff, or a very low cutoff frequency, you need a large room with very deep wedges. And in order to measure the performance of those wedges, you have to build a very large impedance tube. Typically in a standard tube, impedance tube, it's going to be 29 millimeter or up to 100 millimeter diameter sample. But when you're testing these very deep wedges that are 3 feet deep or more, you need like a 4 by 4 foot cross-sectional area and a 40-foot long impedance tube. So it can be done. It's just you just have to scale it up.
Thank you so much for explaining. Going back to the kennels, an audience member, they said, thank you for talking about the kennels, but their situation would be indoors. They said, I'm put over 100 dog kennels in an existing metal building with very tall ceilings. What products would you recommend? Some preferences must be washable, rust resistant, and not harbor bacterial growths.
Oh yeah. Okay, that's a great question. So you bring up something that I don't believe I mentioned yet. Ceiling baffles are going to be pretty useful in that scenario. This kind of metal faced wall panel as well. What we can do is inside of this metal perforated panel is the acoustic insulation. We can put a bagged layer, like a polyvinyl wrap around the insulation to keep it from getting, you don't want to spray it down with a 3,000 PSI pressure washer, but if you have a garden hose or something, you can spray it down and that'll not affect it too much. So it is washable, easy. They're pretty easy to clean. You can wipe them, the front of them with the cloth. And if you want to protect the insulation, you can just bag it. So that's what I would say for the wall treatment. And then on the ceiling, you can put baffles that are water resistant as well.
Thank you so much, Andrew. Next question, when would we use a barrier versus an absorber?
Yes. So the barriers are used when you want to keep sound out. An absorber would be used when you're trying to reduce the sound of what's in your existing space. Hopefully that makes sense. I know it sounds kind of simple, but that's basically what it boils down to. If you have a composite, you're essentially trying to do both, right? When I was talking about composites, this is an example of a we call it a barrier wall, but it's a composite, right? So you have your sound source inside this wall enclosure. So there's a perforated side on one side that helps to absorb the sound, the direct sound emitted from here. And then there's also a barrier as well to keep the sound from, keep the outside or keep the noise from getting to the people out here. Hopefully that makes sense.
Yes, it does. Thank you so much for clarifying.
Sure.
Next question, what types of materials and manufacturing processes can be used for outdoor barrier walls to prevent corrosion?
Oh yeah, that's about the number one issue that can come up. Actually, this is probably a pretty good example. Oftentimes we'll use a galvanized, a G90 galvanized steel. So it's steel with the coating, and then we'll put a powder coating on top of that to prevent corrosion of the steel materials. This usually the support steel, the steel columns is going to be zinc coated. Let's see if I have a good picture of one of these. That shows, so the other thing we do, so this image on the left here, it shows a rooftop barrier that's covering a HVAC or chiller system. If you look closely, you can see that the wall panels are all raised about 4 inches off of the ground, and that's to help keep the bottom of the panel, this bottom panel, from sitting in any sort of precipitation, snow or standing water, things like that. The other thing that I want to add is the manufacturing technique of these barriers is really important. When you spot weld, you can introduce potential corrosion contact points. And when you spot weld something, powder coat that doesn't necessarily stick quite as well. So we don't use spot welding. We button punch all of the panels together. So that way you really mitigate any potential corrosion problems from that spot welding can typically cause.
Got it. Thank you so much.
Yeah, no problem. I was going to say it's a combination of the placement of the product and the manufacturing techniques.
Got it. Thank you so much. Next question, what is a good acoustic level to achieve in a manufacturing environment?
Oh yeah, good question. Well, OSHA says somewhere around 85 or 90 dBA, depending on how long your exposure is. Most of the environmental health and safety people that I talk to want to be a little less than 85, and for good reason. Usually, you want to be able to have a conversation with somebody out there. Noise conservation hearing programs, which are usually the solution to a noise conservation hearing program is usually to have the people wear earplugs, and sometimes it's really hard to enforce that all day, every day, 100% of the time, and so really the EHS folks try to make every effort they can to help reduce either the path or the sound source itself, so that way folks don't have to wear earplugs constantly. And there's safety reasons for that. Folks don't want to lose their hearing, obviously, but they also want to be able to hear other things around them. So 85 dBA is sort of the bare minimum level for an 8-hour shift that would be that I see a lot of people target. But comfortably 70 dBA I think would be a good level to at least target.
Great, thank you so much. What is the typical process for developing a noise control solution for enclosures?
Yeah, there's a lot of ways to go about doing it. A lot of times customers will have a noise control product built into a specification. If not, and a lot of what I do specifically is somebody will call up IAC and say, hey, we've got a noise. I'm not sure what to do. Can you take a look? And so the first step is to have a conversation, and the second step is to go to the actual facility or go to the spot, take some sound level meter measurements, just some real basic stuff, and talk through the customer, look at budgets, look at timing, look at what is going to fit, and see what kind of solution is going to work for them. And oftentimes we're working with a lot of people. A lot of the manufacturers don't have acoustic people specifically that work with them. So I work with a lot of the environmental health and safety people. I work with a lot of facilities people, because you need to be able to have access to the equipment to be able to do maintenance, and make sure that we have a maintenance plan in place that doesn't cause the person to spend 2 days fixing a problem rather than 2 hours if that enclosure wasn't there. So we want to make sure that it's as user friendly as possible.
Thank you so much. Before we go to the next question, can we switch back to the contact slide?
Yes.
Thank you. Awesome. Thank you so much.
There we go.
Amazing. Back to the enclosures. What is the range of noise reduction that can be achieved with enclosures?
Yeah, I mentioned earlier, we can get up to STC 70. That's with a double wall metal wall enclosure. Depending on what sort of sound source you have, that can range between 55 all the way up to potentially 70 dB of noise reduction. So if you're in a manufacturing plant, and you're at 100 dB, you put this double wall enclosure up, you can get down to roughly, if I do the math right, 30 to 45 dBA.
Wow, thanks so much.
Sure.
Are all of the components acoustically rated, like doors, windows, and ventilation components?
Yes. Everything is going to have some acoustic performance. Usually that comes into an NRC value or an STC value. When it comes to HVAC system, louvers and silencers have something called an insertion loss value, but it's going to be very similar. The insertion loss value is similar to an STC. It's a different test method. It doesn't use the same test method that we use to calculate STC.
See, thank you so much. Can I install the materials myself?
Sure. We provide materials all the time. Depending on the level of complexity, it can get pretty scary if you're building a full metal enclosure with a bunch of other acoustic treatment yourself. But if you're just hanging ceiling baffles, or if you're putting up wall panels with some absorption, it's pretty easy, pretty straightforward.
Thank you so much. And I heard you mention this, just wanted to ask about it. What is a dB compared to dBA?
Yeah, that's a good question. And you always want to ask, if you get any sort of sound levels, you always want to make sure you know what it is. If it's in dB or if it's in dBA. Oftentimes you might not know, or it might not be clear, or it might be dBA, but you know, you're assuming it's dB and vice versa. So the dB level would be a flat line here at 0. That would mean that there's no amplification or no change at any frequency. That's dB. When you apply the A-weighted curve, that's this blue line here, all that is it's like a filter. It's a digital filter that's applied when in any sort of sound measurement, like a sound level meter, for example. It'll have this A-weighted digital filter built in. So what it does is it reduces or amplifies the sound depending on what frequency it's at. Because we're not very sensitive to sounds at low frequencies, the A-weighted curve will reduce. So for example, at 100 hertz, let's say you measure 80 dB. Well, at 100 hertz, that's roughly 20 dBs less on the A-weighted scale. So 80 dB would be at 100 hertz, 80 dB would be equivalent to roughly 60 dBA. And the reason that we do this is to try and mimic how we hear, because we're more sensitive at these mid frequencies and not so much at low and very high frequencies. This is an attempt to mimic how people perceive sound.
Got it. Thank you so much. Next question. How does low frequency sound reduction methods differ from high frequency sound reduction methods?
Yep, good question. So low frequency, if you can imagine a sound wave traveling through the air, low frequency sounds have a very long wavelength. And so being able to absorb that sound, you need a very, very thick acoustic absorber to do that. Conversely, in very high frequencies, you can get away with a very thin layer. So it's really important to know what you want to do, and to know how loud your sound is, not just with a single overall dBA value, but to know how what your level is at every frequency, at every octave or third octave band at the minimum. Because if you have very low frequency noises, then you're going to have, if you're applying a barrier, you need a block sound, it's going to have to be very, very heavy. If you have an absorber where you're trying to absorb sound inside of a room, then you're going to need a very, very thick absorber to be able to do that. But if it's mostly high frequency or even the mid-level, you can use more standard, 2-inch or 4-inch thick absorbers, and you don't have to use 1/2-inch thick steel plate to line the walls of your room. You can use a much more, we don't want to over engineer it if we don't have to.
Makes sense. Thank you. You touched upon outdoor basketball, but what about indoor with arenas? You're essentially trying to do both. You're trying to keep the sound inside, but also trying to stop it from going outside. Are you using a mix of barriers and absorbers, or is there a specific one?
Yeah, most of the time in gyms, they're built with the CMU or poured concrete, so they're pretty good at keeping the sound out. But obviously they're pretty large, and so you need some absorption in here. Typically for arenas and gyms, I see just absorption is often used most of the time. Yeah, it just depends on the construction of the walls. If it's just a single or double layer of drywall, it's probably not going to have a real high SDC level, and maybe you want to consider adding some barrier, like a vinyl barrier on one side or the other of it. But usually for these big spaces, it's mainly just has to do with the sound that's generated inside the room from the audience, from the fans, and making sure that you can minimize the echoes in there.
Great, thank you so much for explaining. Next question. How does one specify an acoustic performance requirement?
Yeah, that's a pretty general, that's a probably a whole nother webinar. It really depends on what you want to do. I know I hate saying it depends, but it really, like, if you're trying to, keep sound from escaping, then that's a different sort of solution than if you're trying to do the opposite. Essentially, it's keeping it quiet on the inside. So, like, for anechoic chambers, for example, you want it to be really, really quiet inside that anechoic chamber, so you can do your acoustic testing and all the noise that's on the outside doesn't mess up your measurements. So you want to have a very, very low noise floor inside. But if you're in a factory and you're enclosing a compressor or some big piece of equipment, it's kind of the opposite, right? Inside your enclosure, it's going to be really, really loud, but outside, that's what you're trying to keep quiet. And so the solution is going to be, quite a bit different.
Thank you. And lastly, is there anything you'd like to add that we didn't get to cover in your presentation?
Oh man. Well, yeah, if there's any other questions that I didn't get to, I appreciate all the questions. There was a lot, a lot more than I thought there would be. So feel free to follow up with me. Let me bring my contact slide back up. And if there's any, if there's any other questions or anything specific you want to get into, I guess in general, noise control is very, very specific to what you're trying to do and the location, the site, the size, the scale, what your budget is. All those things factor into what the noise solution is going to be. It can be something really simple that's already specified from an architectural drawing. Say, hey, we want these panels, there it is. Or it could be, somebody, like I mentioned earlier, somebody calls you up and says, hey, I've got this noise issue, I need you to come and take a look. And then 9 times out of 10, there's multiple ways to solve the problem. We just have to work with the end user to understand what the best solution is going to be for them.
Great, thank you so much. And this is a great topic, and that's why we had such an engaged audience who had
I'm glad. I'm glad there was. I appreciate it.
Thank you. We appreciate the topic. Thank you, Andrew, for answering all our questions, and thank you to everyone who joined us today. That was all the time we had. If you need to reach out with any additional questions, Andrew's contact information is currently in the chat. Just a reminder, after you shut down Zoom, you'll be taken to a survey to provide feedback on your experience today. Please take a moment to complete the survey as it helps us to continue to serve your needs in the future. On behalf of the Construction Specifier and IAC Acoustics, thank you again for joining us and enjoy the rest of your day.
Thank you.